tight until then. All right, just going to give one more minute here for people to join. We'll get started soon. All right, welcome everybody to the final installment of the DOSITS 2025 webinar series. Today we have with us Dr. Brandon Southall and Sana Izajuno, who are going to be presenting Ecological Risk Assessment Frameworks, a spectrum of approaches, assumptions, and applications. This will be a joint webinar where both of them will be speaking throughout today's session. So that's exciting. We'll get to hear from both of them. Before we come back and introduce the speakers, if you are joining us over Zoom, you should see something like this on your screen. Near the bottom of your screen, you'll see a tab for audio settings. So we do have AI closed captioning turned on. So if you would like to turn on subtitles for yourself throughout today's talk, you can choose to do that in that tab. You'll also notice there is a chat box button and a Q&A panel button. The chat box is something that is for all participants to talk to each other, say hi, discuss the topic informally amongst yourselves. And then if you have a question for us for any of our panelists, you can drop that into the Q&A box. So if you click on the Q&A icon, a little box will pop up and you'll see an area for you to type in your questions. Those questions will be visible to all of our scientific panelists as well as our speakers. And we will answer them throughout the talk. If there are any questions that are very specific to the topic being presented, then we will leave that for our speakers to answer towards the end of the session today. So feel free to drop all your questions in there. If you're joining us from YouTube, we also do care about your questions and your inputs. So if you type in any of your questions into the YouTube chat box, our panelists will also be able to copy that into the Q&A session or the Q&A box for the panelists and the speakers to answer throughout the session. So with that all said, please welcome Dr. Sana Izojuno and Dr. Brendan Southall today to present their talk. Dr. Sana is a researcher with the Sea Mammal Research Unit and is involved with marine mammal acoustics research at the University of St. Andrews in Scotland. Her research focuses on quantifying the potential impacts of human activities on the behavior and space use of marine predators, including marine mammals and seabirds. So we'll hear a little bit about that today. And Dr. Brandon Southall is a president and chief scientist for Southall Environmental Associates, which is SEA, and has various positions at research institutions and companies around. He's contributed a lot of research in the area of marine mammal behavioral responses to sound. So we will hear a little bit about that today as well. So please welcome both of our speakers today. And with that, I will leave it to both of you.
Great. Thank you so much. There you go. Can you give me, there we go. Yeah, thank you so much. It's great to be here with the DOSITS team again. It's awesome to see so many people from all over the world. I saw the places pinging in on the chat there, which is great. I think if you're new to DOSITS, which most people on here probably are not, but if you're joining for the first time, I strongly encourage you to check out the website and all the resources that DOSITS has. I think it's one of the best resources that we have in our field in the world, and I've been happy to be able to be involved with a number of efforts and webinars, and happy to be here today. I'm going to give kind of the first part of this, an introduction and a little bit of my experience with some of these kinds of approaches, and then Sana will speak after me, and then we'll take some questions together. So we've collectively been working on this kind of approach of taking ecological variables and risk assessment kind of frameworks and different types of approaches into account to try and answer regulatory questions and help inform regulators and give them tools to be able to help make decisions, and industries to be able to comply with and evaluate their own kind of operations. So I think some of the ideas from this really grew out of some discussions that started maybe as much as 10 years ago, as we were seeing this spectrum of approaches that exist, from things that are quite simple to things that are more complex and fully quantitative, as we kind of evaluated marine mammal impacts. But we came together, Sana and I came together and have been working with a number of other people through this Wildlife and Offshore Wind project. And there's a paper that's kind of evolving out of that project that's looking at these kind of diversity of approaches or spectrum of approaches. And I'll walk through it a little bit. I'm going to be really brief on why do we need this kind of perspective, because most people on this call probably are quite aware of why sound in the ocean is important and is a regulatory and management issue. It's critically important for marine mammals, fish, invertebrates, for a variety of different life functions, and people have been putting into the ocean sound into the ocean in increasingly complex ways, either on purpose or as a byproduct of things. And really, the kind of key questions that we need to answer to get at some of these applied issues, include things like what kind of sounds actually negatively affect animals. How can we make rules for managing them that are reflecting the complexity of the natural environment, but that are realistic and reasonable and applicable and understandable. What are the kind of requirements that are needed for mitigation, the legalities of these things and the differences across. I mean, we saw all the different jurisdictions that people are in. Countries have very different legal requirements for assessing and mitigating impacts. And we're working in a very active field that's changing. So how do we reflect the kind of complexity of the world and animals and context that we're that we're uncovering with science. There's a spectrum of approaches, or there's a spectrum of approaches to assess a variety of different kinds of impacts that we see. And again, just briefly, these sort of go along kind of a severity scale that's increasingly concerning, but decreasingly likely. But the kinds of things we've had to consider, range from things that are really, really minor, or that can be somewhat difficult to understand how significant they may be, like masking, to things that, are clearly more concerning, like, physical injury or permanent threshold shift, and a whole spectrum of things on behavioral responses that also have this, spectrum of severity that might be, at the individual level, seemingly quite, minor or temporary, up to things that maybe are more concerning from a population perspective, like permanent abandonment of habitat. And obviously, mortality kind of events are rare but dramatic, and can have population impacts on local levels, as been documented in different places. And then some of the physiological effects, which are difficult, may not be something that's outwardly evident if there's not a strong behavioral response, but that can be meaningful either way. So just these are the kind of inputs to this means of evaluating different impacts, and it means that we kind of need a way to consider at some level all of these things and balance this variable severity of impacts at the individual and then especially at population levels. So we're seeing some real evolving ways of thinking about these things. When I spent my time working within a regulatory agency in the US a long time ago, there was really this very step function, single numerical threshold based way of thinking about things where, at a certain, sound level, you had a behavioral response. Below it, there was no change. Above it, there was 100% change. And that's really evolved. The world is a probabilistic reality, and these kind of risk functions, and these are the Navy's risk functions for behavioral response for different marine mammal species, kind of reflect the probabilistic nature, and in some ways the sort of um, dual step function threshold reflect the contextual nature, where you have this range where behavioral responses are highly contextual, and then they become more linear at higher frequency, at higher exposure levels. But increasingly, and the focus of our discussion today is really around using a variety of different analytical frameworks that take into account um, aspects of species populations, contextual factors, other things like what is the context of the exposure that animals are in, what are the states that they're in, their behavioral states they're in, what are the population level states that they're in relative to other factors than just noise exposure, and to try to be take into account some of the more of the complexity that exists in the world and the reality of how animals live, and point towards more population level kind of outcomes. So if we had everything we would want to be able to make this kind of assessment, we would know exactly, when and where animals were, the kind of, environmental factors that influence their spatial and temporal distribution. We would know all of the aspects about exposure of different types of sounds. Those could be incorporated into an exposure model. We would know what the spectrum of responses are either from a behavioral or a mortality kind of perspective, what those individual effects are, and then how those kind of effects would translate into health and more and protracted effects. And we would know what the consequences are as they relate to vital rates and things that matter in terms of the survival and fecundity of different species. So that's what we would like to know to fully evaluate these things. The problem is in most instances, we don't have some, or in some cases, really enough detail on any of these things to be able to fully parameterize some of the most, fully quantitative population models that have been developed. We would ultimately like to have those kinds of models and these kind of input data, but it doesn't always exist to get to these kind of population outcomes. Um, and again, there's as you move down this, there's kind of an increasing level of uncertainty, both in terms of the input parameters and how they relate to populations. So we have proposed or are proposing that there's a place for some of the more simplified assumptions in certain contexts, and there are goals to be able to get to population level effects from um, a fully parameterized quantitative way. And this is just kind of a conceptual model. And as we go through this talk, you'll see some examples that go along these spectrums of things that go from, qualitative kind of assessments that are essentially just scoping, an area and what types of species are there, what kinds of broad patterns are they resident animals? Are they migratory animals? Are there endangered species there? Yes or no? Up to things that are more risk ranking and prioritizing kinds of questions that start to include aspects of population parameters and other stressors, and then up to things that are a retrospective kind of impact assessment and validation, things where we can quantify impacts with more fully quantitative and parameterized models. Okay, I'm going to talk just briefly about one of the ones, the assessments that I've been involved with that's kind of in the middle of that spectrum, but it's an example, a paper we published a couple years ago that uses this relativistic index, which is a quantitative integration in space and time of the relative space, time, and sound frequency intersection between exposure and animals. And there's equations I'm not going to go into, but that are in that 2023 paper that go through how that space, time, and spectrum intersection occurs. The time is scalable. We used a monthly approach. We've used annual for others. You could use daily if you had that level of resolution. And then the other axis includes these aspects of populations, how they're trending, what the total numbers are, how the species uses habitat, how compensatory they're able to be. Aspects of masking have been part of it. In some applications of this, and then other stressors, what's happening in the environment that the animals are already exposed to that isn't noise. And this is it's a quantitative integration of quantitative metrics as well as some subjective expert elicited metrics that are integrated using this quintile kind of approach to give you a relativistic rating that can be run across multiple different species. So this is just an example from the paper where we could say if we're installing, wind farms off the East Coast, what happens if you start in March versus you start in July, and what happens if you drive piles only during the daytime or you drive piles continuously, and how does that relativistic index scale using those different assumptions. And one of the strengths of this, I think, is it allows you to make multiple kinds of comparisons and scenarios across different species. And you see that, sometimes there's winners and sometimes there's losers. So you have to make some decisions about, do I care more about right whales than gray seals? And if you do, the best thing you could probably do in this context would be to start in July and drive piles continuously because the animals are not there during that period of time, for instance. So this gives us the ability to make those kind of assessments. We're right at the threshold of operationalizing this into an R Shiny tool that allows you to do this across 18 different species and all these different contexts and scenarios with uncertainty estimates plotted on it. This project kind of got caught up in the some of the grant termination things ending, so it's right at the finish line of operationalizing this tool, and we're hoping we can find ways to pick it up to finish it for the East Coast of the US and then extend it to other applications in other parts of the world. But these are the kind of tools that we could use. We could hand to managers and say, run these different scenarios and see what the trade-offs are in terms of vulnerability and sensitivity of different species. Okay, I'm going to turn this to Sana at this point, and really here's where we're going to pick up on some of these other ways of looking at the spectrum of models across these kind of mechanistic and up to heuristic models. And I will let you take it from there, Sana, and I'll go into the background and forward slides for you as you go.
Thank you, Brandon. So this slide aims to, again, kind of illustrate the spectrum of approaches or analytical approaches in particular, which you can kind of conceptualize as each consistent of a different mixture of components that can be mechanistic, very data-driven, so empirical, or that they might have some more heuristic components. So mechanistic models aim to replicate the causal pathways of impact in the risk analysis as closely as is feasible given data constraints and knowledge constraints. Then more heuristic approaches then can be considered to kind of shortcut some of these causal pathways of impact. And this is where some of the scoring algorithms can include more heuristic components, though they are often very data-driven as well and can be structured in a way that replicates some of these mechanistic models as well, like a simulation model such as individual-based model. And then very empirically driven models, you could think about species distribution and habitat modeling, for example. But for now, I'm going to give you an example of a comprehensive assessment that is more at the mechanistic end of this spectrum. Next slide, please. So this work is part of Grace Edmondson's PhD project. She's based at St. Andrews at the Center for Research into Ecological and Environmental Modeling, or CREAM for short, and her supervisors are Len Thomas, Lindsay Scott Hayward, and myself. Grace and also Len are online in the webinar today and ready to chip in the discussion and answer questions as they arise. So this risk analysis was carried out for the US East Coast for 12 cetacean species that have monthly density distribution estimates available. So these density distribution maps are updated regularly by the MGL team and are available freely online. So the risk analysis starts with the occurrence box by drawing individual locations based on those monthly density maps. Next slide, please. So the exposure scenario in Grace's model consists of a turbine installation schedule in the future, source level for pile driving, and a simple propagation model that assumes a mix of spherical and cylindrical spreading loss. So 17 log R, but also accounting for factors like absorption loss. So linking with the propagation model is the individual locations. So Grace has been testing different ways to simulate individual movements. And there's the monthly movement model, where individuals are assumed to remain in the location for the month and then kind of jump to the next location as the month changes. There's a daily movement model where individuals move slowly between locations, so interpolating between points and adding some jitter to add some non-linearity. And this is shown in the figure here. What's not shown here, but she's also considering a kind of worst and best case scenarios for movement where some individuals are consistently closer to pile driving and therefore more exposed than other whales. Next slide. So with these individual locations and the propagation model, it is then fairly straightforward to apply a dose response function to calculate the probability that an individual will show a behavioral response, such as avoidance. And then you can essentially toss a coin according to this probability to determine whether the individual responds at that day or not. So this is kind of the probabilistic method that Brandon mentioned earlier. So because Grace's simulation is individual based, the location and exposure of each individual each day is known. You can then sum the total days of disturbance for each individual over time. Next slide. So the total number of disturbance days is an aggregate measure of disturbance, which we can use then to proxy the long-term fitness consequences of disturbance to each individual. So the simulation follows the interim population consequences of disturbance, or IPCOD framework, where the relationship between the total disturbance days and the effect on individual survival or fecundity, depending on species, comes from an expert elicited transfer function. So once you have a function, you can calculate how much the survival or fecundity is decreased for each individual with increasing number of disturbance days on the x-axis, with some uncertainty estimated from this elicitation process. Next slide. So in the final step, this reduction in survival or fecundity can be incorporated into a stage-based population projection model, Leslie matrix model. So the stages here include calves, juveniles, first-time reproducing females, and other females. These female populations then are projected in the future under two scenarios, with and without the disturbance impact. The difference between the two then provides the counterfactual of change, and it's an absolute measure of potential population level consequence. And this can be measured in terms of population abundance, for example. Next slide. So Grace has carried out this IPCOD assessment for a whopping 12 cetacean species with these monthly distribution maps available. As well as that, she has also applied a structure scoring approach for the same 12 species in the region, replicating Brandon's relativistic risk assessment framework, but aligning the input data of the two approaches so they are as comparable as possible. So then by ranking the species and exposure scenarios from both approaches, you can then compare the results directly. Now, this cross-validation work is still ongoing, but we are super excited about the first results, as they are already giving clues about where each approach might give similar or different results, and perhaps how each approach could be improved going forward in the future. Next slide. So talking about future. So for the rest of the talk, I'm going to talk about approaches to risk analysis in data poor context and some recommendations for ways forward. So common approaches to deal with data poor contexts include adjusting the objectives of the risk analysis, pooling some input data and parameters, use of proxies, simplifying models or the causal impact pathways, and quantifying uncertainty in the input data and models. And I'm going to walk talk each of these in turn. Next slide. So when you lack data, the first question really is to ask, do you really need the data to answer the question at hand? Or do you need to adjust your analysis objectives so you can use the data that you actually have? And of course, the analysis objectives vary by the stage of the assessment. So we already heard from Brandon about the scoping stage of assessments and prioritization stage. And scoping really is just determining what receptor groups and exposures should be included in the assessments. And often as part of this, there's screening assessments. So evaluating which pathways of the occurrence, exposure, response, consequence pathways are likely to be the most or least impactful, and then prioritizing the most important pathways for further analysis and monitoring. Now, the data requirements for the scoping and screening of impact pathways are generally not as demanding as fully quantifying those impact pathways. Next slide. So to understand this, it's useful to distinguish between what we mean by absolute risk, a relative risk, and ranking of risk. So absolute risk can be defined in very general terms as the likelihood and consequence of some outcomes to populations, where the outcomes are not necessarily all negative. There could be some positive outcomes as well. So absolute risk is then the absolute value changes to the outcomes of the population, like in the IP code example before, the counterfactual in population size, for example. By contrast then, relative risks benchmark risks against some assessment targets. So one way we've quantified this before is to use risk ratios. So with expected level of risk in the numerator benchmarked against some allowable levels of risk in the denominator. For example, if you have expected fatalities in a population, divide that by an allowable number of fatalities in that population. And as long as your benchmarks are robust, then the relative risk can tell you something about the magnitude differences in risk between different species or scenarios. So in the risk ratio example, you could compare species by how close the expected level of fatalities come to the allowable levels. Risk ratios exceeding 1 would be exceeding the benchmark. Now, risk ranking is different. Here we only rank order scenarios or species by their risk. And rank orders really can't inform about the relative magnitude differences in risk. But as I mentioned, the advantage is that risk ranking is generally not as demanding of input data. For example, stating something like a right whale is a greater risk of disturbance than bottlenose dolphin in particular place and a scenario generally requires less information than stating something more specific about the magnitude difference, like they are 5 times at greater risk of disturbance than bottlenose dolphins, just as an example. Next slide. So in adjusting, considering objectives, it's important to consider what the assessment endpoints of the risk analysis are. What do the outputs mean and how they relate to decision-making objectives. And as Brandon mentioned, the further down you go in these impact pathways, the more data and assumptions are required and the more uncertainty accumulates. So when you don't have a lot of data, it's very imprecise. It's then worth considering whether some assessment midpoints in the earlier stages of this pathway would be sufficiently precise while also supporting decision-making. So, for example, at the exposure box, you could consider the proportion of individuals with inaudible range of pile driving, or at the response stage, the number of individuals that are expected to show behavior response. And in fact, the estimation of takes as defined by the US Marine Mammal Protection Act can be considered as such an assessment midpoint. And so it stops short of estimating the population consequence, but it's still a useful assessment metric for decision making in this particular policy context. Next slide. To the next approach, pooling and grouping. So when we lack data, we often resort to pooling or grouping species by some shared characteristics. For example, instead of requiring species-specific audiograms, we may use hearing groups. These groups can be very data-driven. So behavior response studies have shown that behavior responsiveness of different species do not necessarily align very well with the hearing sensitivity alone, and can support different groupings that are based on the behavioral responsiveness. So this is just an example, R package called Espresso that's specifically developed to select appropriate species groupings for multi-species dose response functions. Now, while single groupings are convenient, and they are unlikely to be enough to represent the diversity that we see in different species responses. So we can instead of think of these groupings as kind of species traits, which may be multiple. So trait-based approaches to risk assessment have been advocated to support decision-making when we lack species-specific data. While we don't really have the time to go into the pros and cons of these approaches, we've included a couple of useful references in the resource page for this webinar. Next slide. So next up is the proxies for usage. This is actually very similar to grouping. So in fact, you could consider groupings as a type of proxy where one species is used to proxy another. For example, if you lack distribution data, you could use the distribution of a similar species or a group of species to proxy the distribution of the species that you don't have the data for, and to be informed the blue occurrence box. But even when you have distribution data available, it's really good to keep in mind that they are actually only a proxy for the animal space use as well. And this proxy is so universally used and widely accepted in impact assessments that it would be easy to forget the key assumptions here. So first of all, density distributions can't really tell us whether many individuals are disturbed a little or few animals are disturbed a lot. So the aggregate exposure question that I mentioned earlier. So often these assume perfectly mixed population, that all individuals are the same, which can lead to unrealistic assumptions about individual ranges and movements, because individuals in general don't range the entire population range, especially at shorter time periods, simply because of their movement capacity, but also factors like site fidelity. Density distributions can also underrepresent important movement routes, path corridors, commuting rates. So places where animals need to go, but only spend quite brief amount of time there, and therefore don't really show up in density maps. So in the blue occurrence box then, we don't actually really need the density of animals per se. Of course, we need to know how many animals there are as proportion of population at least, but we also need to know how often they are there, for how long, why they are there, and of course, if there are any trends in occurrence over time. But in reality, most of the available data that we have is cross-sectional, so sampling different individuals without knowing their identity, and snapshots, so with limited temporal coverage. So we really need tools to estimate aggregate usage and exposure from these kinds of data, which is why we are excited about Grace's PhD work to estimate aggregate exposure from these monthly density maps. Okay, next slide. So onto those simplifying models or impact pathways. So models, of course, are always simplifications of reality, and similarly, it is often possible to simplify the number and type of impact pathways in a risk analysis. And not all impact pathways or their components are going to be equally influential on the outcomes. And this is something that can be formally quantified in statistical sensitivity analysis. Now, the example I provide here is collision risk in birds. So here, the risk of exposure is to a contact with turbine blades in air rather than underwater sound. But I hope this can demonstrate the same principles apply for different exposures such as sound. So in the mechanistic end of the spectrum, collision risk models are typically individual-based and very parameter-hungry models, requiring information about turbine design, wind farm activity, wind speed, and for each species, things like morphometrics, flight altitude, speed, micro-avoidance rates, for which actually there is actually very little empirical data to properly inform. And collision risk models really aim to quantify absolute risk to species, so number of fatalities for a given exposure, scenario, and time period. At the other end of the spectrum, collision risk to different species also evaluated using more heuristic algorithms. And these involve various structure scoring systems, some only including 4 parameters per species, which is attractive in data-poor contexts. But the algorithms vary, and it's not very easy to choose between them. So like, should you multiply or add some scores together? So for us then, in the WOW project, the key question is there a middle ground? Can we simplify the collision risk models to require fewer parameters? And we have done quite a bit of testing for this in some seabirds case studies, and the short answer is yes. The outputs of these individual-based collision risk models can be approximated by fairly simple relativistic indices that still mimic the basic structure of the collision risk model, but requires as few parameters as some of the structured scoring systems, so about 5 parameters. And we can show that these simplified mechanistic indices can proxy magnitude differences in risk between different species, even though they don't give absolute risk. So comparing these to the structured scoring systems, we find the structured scoring systems are still pretty good at ranking species risks as well, but they don't reproduce these magnitude differences, as you might expect. And some of them produce quite different results from the collision risk models, as well as there was variation between the structured scoring systems. So the reasons behind this are at least twofold. So most of the structured scoring systems do not aim to replicate the actual impact pathways in question. So there's this uncertainty about the structure of the algorithm. Also, the discretization of continuous input data into scores, like proportion of time spent flying, is data that people use and then convert into scores about daytime activity. And this results in quite significant loss of information that you are not using. Okay, next slide. So finally, the 5th approach, considering uncertainty. So lack of data rarely means no data, but rather uncertainty about what the input parameters are. And in such cases, we can consider the input parameter as not a single value, but a distribution of plausible values. And this can be treated in a fairly straightforward way in almost any kind of risk analysis via bootstrapping techniques. So this involves resampling from the distribution of plausible values for each input parameter, rerunning the risk analysis with these new input parameters many times, and thus generating a distribution of outcomes. So the uncertainty in the input data is propagated through the risk analysis and represented in the width and shape of the outcome distributions. So imagine you have a counterfactual in population abundance in the distribution. So we have now generated a plausible distribution of these outcomes using the bootstrapping technique. The height of each bar essentially represents the likelihood of that outcome, and the y-axis is the consequence. So the greater the change, the greater the consequence. So this is our basic definition of risk. But what we often see assessments consider uncertainty in terms of precautionary input data or scenarios. So running a risk analysis, maybe a couple of different ways with these worst case parameters. The issue with this sometimes can be if you use a combination of worst case input parameters, you can actually end up with quite some unrealistic combinations and outcomes. So if you're lucky, you might end up with an outcome that is at the tails of this distribution. So like the actual worst case scenario that you are aiming to represent, but it could also end up pretty much outside this distribution of plausible outcomes. So we really recommend using these kind of bootstrapping techniques instead and considering the distribution of outcomes to find the worst case and most likely outcomes to inform precautionary decision making. Okay, next slide. Okay, just to recap. So when we are setting the objectives of risk analysis, it's important to clearly define the assessment endpoints or midpoints and what comparisons can be made with these metrics, absolute, relative, or ranking of risk. We'd like to see more empirical evidence and validation to support the use of species groupings and proxies, including proxies for aggregate usage and exposure. And when simplifying risk analysis, it's important to consider the causal pathways of impact. Mechanistic models can be very simple too, and are likely to be more effective than approaches that shortcut causal pathways. And if you're shortcutting these causal pathways, it would be good to validate them as much as we can. And finally, we hope to see more explicit treatment of uncertainty and propagation of uncertainty to consider a realistic set of outcomes. Next slide. So revisiting the spectrum of approaches, we find kind of a hierarchy of preferable options with kind of realistic and parsimonious, validated, tested models on the top, with perhaps mechanistic models with some more simplistic assumptions in the middle, or models with tested heuristics, but where the transferability of models might still be uncertain. And at the bottom, more iterative and post-hoc algorithms with untested heuristics that might still be useful for reaching consensus decisions or decision making, but are further away from formal risk analysis. But whichever the approach, there's a real need to consider uncertainty, both in input parameters and the model structure. And as I said, going forward, more cross-validation of different approaches would be great. Okay, next slide. And that was our last slide. I just wanted to thank you for listening. We welcome all your questions and very grateful for all the co-authors and contributors of this work.
Awesome. Thank you, both of you, for the very informative and very enriching talk. We only actually have one question in the Q&A, so I'll just read it back to the group. The question is, what are the socioeconomic consequences of 5 different model complexities on reducing collisions of marine mammals and top predators with ocean wind farm approval by regulator, wider concerned public? If you need me to copy that in, or if you can see it, do you have any response to this question? Or maybe we can ask for some clarification from our audience member as well.
I mean, maybe I'll start on it just because some of the approaches that we've developed have been specifically trying to look at offshore wind developments, and include some considerations of other stressors like vessel strikes, right? So we know that in some of the lease areas off the East Coast, the primary source of mortality that's stressing some of the populations is vessel strikes from commercial vessels associated with large ports there. So that that factor, that stressor within the context of that that kind of risk assessment is, there's a quantitative way of incorporating that variable, and one of the ways that Sana gave this relativistic risk ranking. In the US, we have a term called PBR, so potential biological removal is the mortality, what can the population allow, or what can the population sustain in terms of removal of animals relative to the population that's deemed sustainable. And there's a long story, and there's variable amount of information and data that supports PBR assessments, but there's a quantitative way that mortality that's associated with something other than the development of offshore wind, which is just existing shipping lanes and the distribution of and changing distribution of whales, and specifically humpback whales in the New York Bight, that's caused this higher rate of mortality. That then the development of offshore wind is an addition to that existing stressor. So I think in that context, the framework we've developed has at least 2 different ways within the what is the vulnerability score, the x-axis of that risk matrix, that's incorporated, which is quantitatively within the mortality relative to PBR for species like humpback whales, and then there's another component that's existing stressors, That's one of, I think there's 8, and there's 2 of them that require an expert elicitation. That's like, what is the relative level of human presence and other noise presence. So it's yeah, it can be incorporated there. I mean, the socioeconomic um, you know, the that I think would kind of be captured by, the regulatory decisions about, when, where, and how these things can be developed, and these tools trying to be useful ways of evaluating. The where part is sort of fixed by virtue of the lease, but the when part I think is particularly and a particularly important consideration and a mitigation component. That's why we looked at things like start time for migratory endangered species. Humpbacks aren't endangered, but other species that are, like right whales. That temporal mitigation is really something that's important. So I think these type of tools are supposed, are intended to give us ways of evaluating things like how can you use time in your favor to be able to reduce risk. Anything to add to that, Sana?
No, I think that was really good. I don't think I have much to add on the socioeconomic consequences, but I just wanted to add on the PBR discussion, because there has been a lot of discussion both in the marine mammal and also seabird literature about when PBR-based take estimates can go wrong. Is that while PBR as a measure of absolute risk may not be perfect, it would be nice to see more simulation studies where PBR is used rather just as a benchmark, as an alternative to something way more simplistic risk assessment. So I think PBR provides perhaps an avenue or something that could be improved going forward to come up with a simplified relative risk metrics when we want to assess different scenarios or different species. So I think there is potential there for further development.
Great, awesome. Thank you for your responses to that question. We have one more that was just added. The question is, how are uncertainties associated with risk frameworks used in the management decisions, if at all? And are usually worst case scenarios considered first?
This is probably for you, Brandon.
Yeah, I'll go ahead and start. I think variable. I mean, I'm speaking mostly from a U.S. perspective, where the more quantitative individual based take estimate and then what it takes mean in the context of populations have been applied. And I would say variable in terms of how the uptake of things like PCOD and IPCOD, or these risk frameworks, but and they've probably informed some of the cumulative effects kinds of assessments under the Endangered Species Act more than things under the MMPA, which are more numerical take relative to what is a negligible impact kind of assessment. But I think increasing interest is what I've seen, and increasing desire to try to use these types of structured approaches in non-marine mammal contexts. They're becoming much more common. So on the West Coast of the US, in a regulatory context, like climate vulnerability assessments for fisheries use these types of either mechanistic or in some cases the more heuristic models. So there's definitely regulatory precedent for that. The risk framework we developed for the offshore wind was part of the regulatory decision framework for the 5-year assessment of oil and gas seismic exploration in the Gulf of Mexico, for instance. So there's definitely things we can point to where they've been applied. I think the more structured and operational we can make them, and I think, as Sana said, having these cross validations for species where we can do the more fully parameterized population models and evaluating how these kind of simpler approaches work in a context where we can make direct comparisons and have a sense of how how valid they can be when you simplify things, that may be necessary to do, right? We can run these on 17 different species on a laptop in 20 minutes or less. That you can't, we're not there, and we're probably not going to get there in the short run to do a full PCOT assessment of 17 species and run 5 different scenarios of time and, operational parameters. So they have their place, but we want to, I think the regulatory application of them will become more widespread, more consistent, and more accepted and acceptable once we have more validation of some of these things. Sana, anything to add?
No, I think that captured it. And yeah, I guess these validation studies would be extra helpful, even if it's in a subset of species, to kind of give an indication of why we might come up with different results, or where they might align and improve some of these relative risk assessment frameworks. But where I think Grace's PhD work really highlights that it is possible to do IP code for such a large number of species, and hopefully that's something that becomes more accessible in the future.
Yeah, I totally agree. I'm really, really happy to see that moving forward, and seeing the cross validation or assessment of that approach relative to this other framework is something we're really excited about. So I'd encourage people to keep an eye out for some of that, and reach out and ask questions of Grace and Len and the SMRU team. I just want to say one other thing on John Cosgrove's comment there. There's a recent paper by Leslie Thorne and Dave Wiley that kind of goes into some of the strike vessel strike stuff on the East Coast relative to the timing of offshore wind. So if you look up Thorne and Wiley 2024 humpback whales, it'll pop up that paper. I could probably even find it and drop it in the chat, but there's yeah, you bet, John.
Right. Well, thank you once again. That is all the time that we have for the Q&A in this session, but I do see some of our participants have added some additional questions that we can have answered by our speakers, and then they will be posted on the DOSITS webpage along with the recording of today's webinar, as well as the transcript and questions and answers from today's Q&A session. So again, thank you to our speakers, and thank you to our participants for the questions and that led to this discussion here at the end. I just have one more thing to go over with the group. If you, as we mentioned, today was the final installment of the 2025 webinar series. So if you registered for today's session over Zoom and you provided an email, you will receive an email after the webinar closes today that has some information about the professional development certificate that you will earn from watching all 4 webinars and participating in all 4 webinars, as well as links to a questionnaire and a survey for the DOSITS team. These surveys help us improve this webinar experience for all of our participants, as well as helps us get feedback on all of our talks. I actually believe those links were also posted in the chat. So even if you didn't register ahead of time, or if you didn't provide an email for today, you can still go ahead and take those surveys and questionnaires. Right, so you'll get, and then once again, if you registered ahead of time, you'll get an email with information about the professional development certificate. And with that, that concludes the 2025 webinar series for DOSITS. Thank you again to all of our speakers and to our participants for joining us today, as well as for joining for the last several webinars in 2025. We are looking forward to the new series in 2026, and I hope everybody has a wonderful Halloween and enjoys the holiday season for the rest of the year.